And now I will stop sharing my screen and pass over to our first speaker. So, Steve, would you be ready to start?
Yes. Okay, just let me see if I can share my screen. Can people see this now?
Yeah. Oh, yes.
Oops. Oh, I've got the spinning Mac wheel. There.
Oh, yeah. Oh, there we go. Now we can see it.
Does that look all right? Good.
Yeah.
So I have this perspective view of the North Atlantic for a lot of my research talks.
Okay.
I spend a lot of time looking at the North Atlantic, and actually, as we will see later in this talk, it looks like the PETM was certainly in part, at least, driven from this region. So Paleocene-Eocene, as we know, they're two chunks of geological time. Oops. It's worth just thinking a little bit about what the world looked like then, just to set the scene. So the world was recognizable back 56 million years ago in terms of the positioning of the continents, but there were some differences. But a significant difference is that we were living in a greenhouse world, or we weren't, but the creatures around then, it was a greenhouse world. So the diagrams here are showing the temperature of the top part of the ocean and the temperature of the bottom part of the atmosphere relative to modern. And there was significant temperature. It was significantly warmer than it is now, and in particularly at the poles. Okay, so the world was much warmer at the poles at these times. So this is exactly the same graph that Mark showed before. We know that over the past 65 million years ago, the dinosaurs died out, and since then we've had a chunk of time called Cenozoic time, and there's been quite significant climate change during that period. So it's shown on this scale by an oxygen isotopic measure, where when you go upwards on this axis, the world was warmer and or it had less ice. When you go down on this axis, it was cooler and or you had more ice. So there's been considerable change across Cenozoic time, but much of it happened relatively gradually. So the descent from the greenhouse world of the early Cenozoic to the icehouse world that we live in now happened in a series of stages, but relatively gradual stages. And the big thing about the PETM, the Paleocene-Eocene Thermal Maximum, is that it's one of the sharpest and biggest spikes on this graph. Okay, so it's the fact that it was a significant event that seemed to happen on a short period of time that makes it of great research interest. So I like this slide to introduce the PETM. So much of what we know about it comes, most of what we know about it comes from the rock record. And here we see a series of cores from the South Atlantic, actually from the Walvis Ridge in the South Atlantic. And the PETM is marked by this striking color change, which you can see in all of these cores. And what that's showing is that the sedimentary rock beneath the PETM is full of chalk. Okay, you can see the calcium carbonate content shown on the blue graphs here. And at the PETM, suddenly all the chalk disappears. And then the chalk gradually reappears or reestablishes itself in the sediments as you go forward after the PETM. So that's showing ocean acidification, basically. Suddenly, there was a significant change in chemical composition of the oceans, and which dissolved lots of calcium carbonate, didn't allow it to accumulate in the seabed. We don't just see the PETM in the marine record, we see it in the continental record as well. So in one example here, the Bighorn Basin, and around about this red, prominent double red boundary there, that's where the PETM is. We also see it even at the poles, okay? So this is just an example. The Arctic Coring Expedition in 2004, busy at its work, and they recovered PETM age sediments showing climate change. So what happened during the PETM? Well, we know from multiple temperature proxies that are derived from sedimentary records such as this, that there was global warming of 4 to 6 degrees C, and it happened in millennia. Okay, so it's on civilizational timescales. It took longer to recover. Maybe we're talking about 100,000 years to recover. And we've seen already from the idea of ocean acidification that the carbon cycle was well out of balance. Okay, in fact, the PETM was originally recognized on the basis of carbon isotopic curves here. You get a sudden lightening. It goes negative on the carbon isotope scale, which is very significant, as we'll see later. The hydrological cycle, there were big changes in that, and in some places, the world got wetter. In other places, the world got more arid, and there's evidence in some cores that we can see for increased erosion and increased runoff. And I've just got one slide here, not that I'm going to describe this slide, but it's a flag to what John's going to say. He will talk in much more detail about the biotic response to this event. There were some extinctions, a lot of extinctions in the kind of planktonic world, and there was overturn of species and migration of species. So I'll leave that all to him, really. But the bottom line is that we think with this series of responses, we think that this was an event which was a global warming event that was driven by supply of carbon-based greenhouse gases to the ocean atmosphere system. And those gases included CO2, carbon dioxide, and also methane. And there's a lot of research effort going on around the world now and for the past few decades to study this event because of its potential use as a partial analogue for modern warming. So this is a reconstruction of the carbon emissions on the PETM, which we'll talk about in more detail later. But importantly, the vertical scale is the same here as this modern record. So there are differences, okay, which do make it a bit difficult to have a direct comparison. There was a lower emissions rate in terms of carbon flux. We've seen that the world was different. You know, it was much warmer then, so we were in a different background state. Any geological deep time record is going to suffer from having a coarser temporal resolution in comparison to the modern records. But there are some potential advantages of looking at deep time. A big one is that with this record of the PETM, we can see the entire warming and recovery, okay? And of course, that's not possible today because we're trying to guess what will happen going into the future. But the big issue is that in order to actually exploit this geological record of warming and recovery, what we really want to do is to try and find out something fundamental about how the carbon cycle changed through that time period. And that's actually really difficult because at the moment, or certainly up till the last few years, there's been a lot of uncertainty over the source of carbon for the PETM. And so there have been various ideas floated as to where all that carbon came from that involve maybe methane hydrates or wildfires or permafrost or kind of volcanic basically and or deeply intruded or erupted magma. So if we're trying to fingerprint the carbon source for the PETM, what are the key observations? So there are two really, and they trade off against each other. So one is the isotopic composition of the carbon that was somehow entering the ocean atmosphere system. And that trades off against the total mass of carbon that was supplied, such that either you can try to explain the PETM by a relatively small mass of isotopically very light carbon, or you can explain it with a much, much larger mass of isotopically heavier carbon. Now, the original work on the PETM was really done on the basis of carbon isotope records. So we only had one constraint, okay, and that was on carbon isotopic composition. And maybe for that reason, you know, they were concentrating on the very isotopically light end mechanism there, which might explain the climate change event with the smallest amount of carbon. And so the leading horse in the race was the methane hydrate horse. Now, you've probably heard of these ice-like sort of clathrate form of methane. It holds a lot of methane immediately beneath the seabed. It's very environmentally unstable, subject to small changes in seabed temperature or pressure via sea level change. You can release this stuff to the atmosphere. But there are problems with that. And one is that, of course, we weren't in the modern world. We were in a greenhouse world. And would really there have been a significant global inventory of methane hydrates beneath the seabeds in a greenhouse world? There's some doubt about that. But more seriously and significantly for that hypothesis, over the past few years, there's been a lot of work to model the carbon cycle throughout the PETM. And kind of the state of the art now is to use sort of ocean atmosphere models of intermediate complexity. So some of these were developed in UEA back in the day. And the great thing about these models is that you're matching not only the carbon isotope records, but also records that can constrain the total carbon mass. So in this case, a pH record across the PETM event, which is derived from boron isotopes. And we won't look at the details of this, but basically that because you're then matching multiple data sets, you can resolve this trade-off. It gives you both the carbon isotopic composition of the emissions and also the mass and the flux of the emissions. So on this graph, over time, over the past few decades, we've evolved from saying, okay, the PETM was probably driven by a small amount of very isotopically light carbon to the paper I just showed you, which is many people feel is about the best estimate we've got at the moment. We're actually looking much more like a much larger amount of carbon, and it's isotopically much heavier. Okay, and that really leads us on to this diagram. Okay, which is that to explain that large amount of isotopically relatively heavy carbon, we really have to be looking at volcanoes. We don't. That's the most obvious place where this carbon could have come from. So how can we explain how the mantle via volcanoes could have driven climate change in the geological past? So this is where my research interest comes in. I've spent a lot of time looking at mantle processes. So the mantle is the layer of earth beneath the crust and the tectonic plates and above the iron core. So it's volumetrically the most significant component of the earth. And it does, although you may not realize it, affect the biosphere, the ocean and the atmosphere significantly. So I like to show this map when I'm kind of introducing how the mantle affects us. This is showing you the topography of Earth's surface at the present day that's actually supported by the mantle. Okay, so there are three things that I want to point out here, really. And one is that every part of Earth's surface is colored on this map. It's either red or blue. Okay, so there is no part of Earth's surface which mantle processes don't really affect at present. Okay, it's a pervasive effect. And the second thing to point out is the scale here. It's labeled dynamic topography, and it goes from -2 kilometers to +2 kilometers. So we're talking about the surface elevation effect that the mantle is causing at present is kilometer scale of the scale of sort of mountain ranges caused by horizontal plate motions and tectonics. And the third thing that I want you to look at is that the biggest colored splodge, the biggest red splodge on this map is here in the North Atlantic, centered on Iceland. Okay, and we are actually sitting on the edge of it right now. So if you don't believe that the mantle has much of an effect on your life, this is what the UK would look like if we didn't have dynamic support from on the edge of this kind of Icelandic mantle convection cell at present. We would all be underwater. So actually, when looking when looking for Darwin quotations, I came across this one. Daily, it is forced home on the mind of the geologist that nothing, not even the wind that blows, is so unstable as the level of the crust of this earth. Now he was, you know, he wasn't really distinguishing between the effects of horizontal tectonics that most of us kind of know and understand, and the effects of support from the mantle beneath. But we'll see that it's actually very true of the mantle, I think. So this pattern of red and blue splodges is supported by motion within the mantle. Okay, now the mantle is solid, and this confuses high school students and even undergraduates. The mantle is solid, we know that because it transmits seismic S waves, but through geological time, it convects vigorously as a fluid. Okay, and this process is called mantle convection. And in some places you have hot material rising up from deep below. Quite how deep is debated, but deep below, and it pushes the surface of the plates up. And in other places you have cold material sinking down, and that pulls the plates down. Okay. Now, the relationship with volcanic activity is that when these convection cells within Earth's mantle, when they initiate, they don't last the age of the Earth. They have a finite age, maybe a few 100 million years. And when these things initiate, they cause episodic huge outpourings of lava, and these are called large igneous provinces. We see them in the geological record all over the world, but the one that we're concentrating on today is the North Atlantic igneous province. Okay. So when I'm doing this talk in a lecture theatre in front of people, we have the guessing game element where I say, oh, well, where is this? Who wants to shout out? But of course, you can't really do that online. But I'm sure many of you will know that that is Giant's Causeway in Northern Ireland. This is a map, BGS map of the North Atlantic igneous province. Fewer people tend to get this one. This is up in the Hebrides, the Isle of Skye, and we're looking there at the Black Cullen Ridge and the Red Cullen here in the foreground. And for climbers, here's the Inaccessible Pinnacle, the Inpin, which is a feature of that Black Cullen Ridge. So this was a magma chamber, basically, that is part of the North Atlantic igneous province in Skye. And most of the North Atlantic province is actually offshore and much of it buried. So here is the island that some people sometimes get. It's Rockall, sticking out above the sea. And this is a map of the whole North Atlantic igneous province. So it's like a sort of summary map, if you like. So the North Atlantic igneous province, kind of the activity began towards the start of the Paleocene, maybe about 60 million years ago. And we saw then some of the formations in the Hebrides, Northern Ireland. But the main period of activity was actually slightly later. It spanned the Paleocene-Eocene boundary. And at that time, Greenland was attached to northwestern Europe. And the main phase of activity of the North Atlantic province actually coincided with breakup of, or separation of Greenland away from Europe. And there was also a large amount of uplift that happened at that time. You can see the coastline sort of stepping out, a land bridge appearing. So that will be relevant to John's talk, I think, later. And all of these, this uplift and this huge outpouring, both of those were being caused by this mantle process that was the sort of development of this convection cell that is now centered on Iceland. And if this association between the North Atlantic igneous province and it spanning the Paleocene-Eocene Thermal Maximum, that is one of many examples through geological time, which Mark referred to in his list. This is basically a graph of Mark's list, really, of relationship between large igneous provinces and global catastrophes. And some of those are mass extinctions, such as the orange ones here, but some of them are climate change events, warming events in the case of the PETM, and some of them are ocean anoxia events. So there's a range of different sort of expressions of global catastrophe, but large igneous provinces always seem to be correlated with them. So raises the question, well, it looks like, or there is a hypothesis that large igneous provinces can potentially cause global warming and other climate change. How do these things put carbon into the atmosphere? And there are two main mechanisms. And one of them is that lava directly releases carbon dioxide. So you can see the gas coming out of these volcanic vents here. It contains a large amount of CO2. And the reason for that is because Earth's mantle has trace amounts of carbon in it. It got there by ocean sediment settling out on the seabed, containing carbon, and then that gets put back into the mantle via subduction zones. But the carbon is incompatible in the mantle, doesn't want to be there. And so the first initial parts of melting to make new oceanic crust, the carbon gets spat out again. And the second and less intuitive source of carbon, here's another guess that I get people to make. We've got a wall snaking across a cliff here. So that's Hadrian's Wall, and it sits on top of the Great Wind Sill. Okay, so that's not actually part of the North Atlantic Igneous Province, but it is an example of an intrusion, a sheet-like intrusion of magma. Not all of magma kind of reaches the surface when it erupts. Some of it stalls within the upper part of the crust. And when it does so, it cooks the host rocks surrounding those igneous sheets. And if they contain trace amounts of organic material, that material is thermally matured and generates methane. It also generates oil as well. And in fact, that thermal maturation process is how we get oil and gas, generally, is how we get oil and gas reserves. Okay. And not only does it generate methane, it also, via a kind of natural runaway fracking process, hydrofracking process, it causes expansion and boiling of the natural pore fluids, and that causes hydrothermal vents blasted to the earth, to the surface, which can release these the methane. So if you're not convinced by that, the answer is, well, we can actually see this happening, and we see it using seismic reflection data. Okay, so this is a kind of echo sounding data which we use to map the interior, the shallow interior of the Earth. And it's this data that forms the basis of the energy industry, basically, the oil and gas industry, and then its kind of modern, maybe more carbon sequestering version. And here is some seismic data from offshore the Rockall Trough in the North Atlantic Igneous Province. And we can see these igneous sills. This is what they look like, kind of highly reflective patches. Okay, and there's a whole load of them shown here, and we can measure their characteristics. And I'm not showing vents here, but we can actually, the best data does show hydrothermal vents, and these things have been dated, the rocks, the igneous sill rocks and the hydrothermal vents. There's a lot of them appear round about the Paleocene-Eocene boundary. Okay, so, but there's a kind of elephant in the room here, isn't there, really? And that, which is not just for the North Atlantic Igneous Province and the PETM, but for all, you know, this general correlation between large igneous provinces and climate changes. And that's that the igneous activity spans millions of years. Okay, so if you look at, we've got the vertical axis of this plot is in millions of years. And if you look at an individual Hebridean island, for example, we're talking, you know, several millions of years for the peak in igneous activity there. Now, that igneous activity does in general span the sort of the general time period when the PETM is happening in this red line, but the PETM itself was much shorter. You know, the onset was around about 10 millennia, possibly less. So the big question is, you know, if it looks like if we were to explain the PETM by the North Atlantic Igneous Province, we have to be able to postulate some sort of pulse of strong, much stronger than normal igneous activity within that large igneous province. And that raises other questions, that how ultimately that magma is all being generated by a mantle process. And how can a rocky layer, you know, move so fast as to melt that fast as to create such a, you know, rapid amount of volcanism? And that's a massive question, you know. So, but finally, in the past few years, we're getting somewhere on that. And the answer, or a clue again, comes from seismic reflection imaging. So this is another quiz that I will give to people if you were all sitting here in front of me. So one of these is a modern digital elevation model of actually part of the USA, the San Andreas Fault Zone, and the other is an ancient buried landscape that's been reconstructed from the interior of one of these seismic cubes. And I asked people to guess which is which, and people, it's always 50-50, which just really goes to show the quality of the seismic imaging. But actually the ancient landscape is the top one here. So this is a landscape, a subaerially eroded by rivers landscape that's now buried deeply beneath the Faroe-Shetland Basin offshore the UK. So there. And I'm not going to go into detail as to how we reconstruct these curves, but based on the sort of geomorphology and of this landscape correlated with careful biostratigraphy, we can get a vertical motion curve for this landscape. Okay, and the time scale is in million years here. And the key point really is that the peak, well, first of all, we're talking about very significant uplift here, like kilometer scale uplift to create that buried landscape. And also the time period, look at the rate of change of these vertical motions. They're really steep. So there's action happening well within 100,000 years and down to the required time scale. There's significant action happening on sort of certainly tens of millennia. So it does give, and this is the uplift that's accompanying the igneous activity. This is the uplift that's being driven by mantle processes. So we do have evidence to say that mantle processes are happening much more rapidly than most people would expect. So how can that be? Because, you know, how can the rocky mantle move so fast? And the key to that is a process called mantle plume pulsing, actually, we think. So if you look at this, it's rather a slow, grainy animation. But can you see this mantle plume here? Can you see here a little blob sort of detaches from the lower thermal boundary layer and shoots up the stem of the plume? Okay. Mantle convection is inherently unsteady. And that's not just mantle convection, that's any high Rayleigh number convective process is inherently unsteady. That leads to this phenomenon called mantle plume pulsing, where hotter and cooler blobs are being advected up the stem of the mantle convection cell, and then they pass through the head of the convection cell. And again, I'm not going to go into details with this, but we can see that process happening right now in the sea floor beneath south of Iceland. So we know that the Icelandic convection cell has these blobs. And my research group have been taking this mantle processes approach to try and see whether very rapid passage of these hot blobs beneath the North Atlantic could have generated that the igneous activity on the required time frame. So the idea is that a hot blob came up underneath Britain and the northwestern Europe in the very, very latest Paleocene, and then spread outwards beneath the plates like ripples on a pond. And so a question arises, well, can we actually see that happening? Now, this process is recorded by the changes in oceanic crustal structure. Basically, mid-ocean ridges record very small and even much bigger temperature changes in the mantle going on underneath. And so a couple of years, well, actually last year, I had an expedition to go and try and find the crustal trace of this putative PETM forming volcanic pulse. And we went out from Ireland to this very poorly explored area southwest of Rockall Plateau to a place called Eriador Ridge. And there's the boat, and here's the crew. So this was a nightmare to organize in the middle of the lockdown last year, but we did manage to do it. We did set sail, and we did get data. And again, in this talk, I haven't got time to go through this in great detail, but the bottom line is we do see a ridge, this molar-like ridge here, is the pulse of volcanic production of Paleocene-Eocene Thermal Maximum age. Okay, so it does look, at least in principle, as if this thermal plume pulsing idea can potentially explain the Paleocene-Eocene Thermal Maximum. And so kind of beginning to tie things back up again to actually how we, can use this to inform climate change and maybe think about the present. We're now in the situation where we can do simulations of North Atlantic igneous provinces, and this is one of them. We published a few years ago, actually. So this is a simulation of the North Atlantic sill province, igneous sill province. Okay, so here's the UK and Greenland, and this white stripe is Rockall Trough, Faroe Shetland Basin, basins offshore Norway. And each one of these red spots is an individual igneous sill being intruded. So this is a stochastic model, and it's kind of underlain by statistics based on the seismic data we were looking at before, and time frames kind of based on those uplift surfaces that I showed you before. And each individual sill doesn't last for very long and doesn't produce very much methane or CO2. But together, if they all intrude within a short enough time period of each other, the cumulative emissions are significant. Okay, and we can compare the cumulative emissions from models such as the one I just showed with completely separate estimates of greenhouse gas emissions from sediment cores, and that's what's shown here. So you've seen this diagram already. So the blue line here, that is a core-based reconstruction. I called it a sink-based estimate there. That's a core-based, sedimentary core-based reconstruction on the basis of a kind of global carbon cycle model of the greenhouse gas emissions. Okay, and the red is my completely separate, or our completely separate reconstruction of what the North Atlantic igneous province could have emitted. And the bottom line here is that there is actually quite a close match, or potentially quite a close match between those two curves. So potentially large igneous provinces can generate the required amount of greenhouse gases in terms of the flux and the mass, and mantle processes can potentially cause these changes in greenhouse gas flux fast enough to maybe explain the PETM. Now, of course, there's a lot of uncertainty, and the main uncertainty is the vigor of the mantle convection cell. So there's more work to be done on that, and it's still too early to say whether the North Atlantic igneous province alone could have done the whole job, or whether it kind of provided a background sort of situation, and then other feedback processes were which made them able to actually cause the PETM. So that's what we're working on at the moment. But kind of just beginning to wrap things up now, really. I think we're getting to the stage, or the great excitement is really that we're getting to the stage where, we've got the PETM as an entire record of the warming and recovery. And now we do actually, there is growing global consensus, certainly, that it's large igneous province carbon is a big player here. And added to that, we've now beginning to develop a physical understanding of how that might actually happen. So I'm not saying that this red curve is the answer right now, but it's, I think over the next 5 to 10 years, we will get a curve like this that most people would be happy to sign up to. And that is really exciting because it gives the potential to reconstruct carbon cycle feedbacks. Because if you've got two separate records of flux, one of them from a sort of sedimentary core-based record that's showing the response of the ocean atmosphere system, and one is the source function, for example, from those simulations that I was showing before, then the gap between those is the feedback in the carbon cycle. And what we really are interested in is, are we in the situation, or were we in the situation on the left where there was a bit of a kick from an igneous source, but that really wasn't doing the main job. Then a whole series of positive feedbacks within the climate system took over and generated the PETM response. Or are we in a situation where actually the response was quite closely coupled to the igneous forcing and the actual feedbacks, and maybe potentially harmful tipping points in the climate system here were less than we might worry about. And it's this kind of understanding of the carbon cycle that I think is really going to be, useful in when we're thinking about what's happening at present and what's happening going forward. So I guess just to end, from my point of view, I can't actually read this because it's right. So, Darwin, Mark was mentioning this, we marvel when we hear of the extinction of an organic being. We don't see the cause, so we invoke cataclysms to desolate the world or invent laws on the duration of the forms of life. He didn't really like this idea of, sudden changes. But actually, I guess, from my point of view, if you take the long view of mantle convection, actually, this is a completely normal process that's happening the whole time. And it's just, this kind of high Rayleigh number convection system, for example, has just blobs that go around it, and that's just the norm. So, well, I guess it's food for thought, really, that we can consider how. But I think we're really beginning to develop an understanding over maybe, we'll do some more work on this over the next 5 to 10 years, as to how we explain this kind of episodic or punctuated equilibrium geological record in terms of both large igneous provinces and maybe in terms of the environmental consequences that go with them. So I think that's really all I've got to say. Is that about the right amount of time, Mark?
Yeah, that's fine. Just slightly overrunning, but we can probably what we could do is